This is the last presentation of the 2016 MOSRP Annual Technical Review and Meeting. We're going to use this opportunity to briefly go over the highlights of this meeting, which represent the progress of this our program this last year. In addition, we're going to provide a perspective, a viewpoint of where seismic exploration has been, where it currently is, and its future. And here's a seismic processing tree, which shows you in the marine setting, very similar for onshore, the different stages or steps in this link chain of processing steps that data undergoes from the time it's acquired to the time it's used to locate and delineate hydrocarbon targets. 30 years ago, the state of seismic exploration and progress in seismic exploration, if we separate seismic exploration in terms of addressing the removal of multiples and imaging and inverting primaries, both of those multiple removal came in two varieties. One had statistical assumptions, deconvolution ideas, predictive decon, and they had statistical assumptions about the relationship of primaries and how primaries relate to multiples. A separate route was a route that sought to separate by some characteristic primaries from multiples. Stacking, FK filters, radon were examples of that approach. In addition, there were an entry into wave theory methods. The first entry into wave theory methods were modeling and subtraction, where people tried to model, for example, the ocean bottom reverberation and subtract the reverberation within the water column by adjusting the properties of the water bottom and seeking to remove that type of multiple by matching the modeled multiple to the actual. And so that's one whole progression. As the methods moved from, for example, stacking to FK filter to radon, there was an increased need for velocity to achieve that. And that is basically where multiple removal was at some point roughly 25 years ago. On the migration route, at that same time, if you want to start in the mid to late 70s, where wave methods first entered migration, there was an evolution of migration concepts where each step in increased effectiveness for migration had an increased demand on subsurface information. When you went from post-stack time migration to post-stack time migration to post-stack depth migration, you got an increase in need for subsurface velocity. When you went from post-stack anything to pre-stack migration, there was an increase in need for velocity. When you went from pre-stack time to pre-stack depth, there was another increased need for velocity. And then when you went from one-way migration to two-way migration with RTM, again, there was a step change in capability, potential capability, but a concomitant need for increased subsurface information. And that progression on both the multiple side and the migration side, you can, in 2003, I had the honor and privilege of being the SEG Distinguished Lecturer and gave a talk about the evolution, that evolution around the world. And in 2005, Bill Dragoset and I published a book of multiple reprint, which traced that evolution of multiple removal methods. So what happened about 25, 30 years ago is suddenly the interest in the petroleum interests exploration and production moved to deep water and to onshore and offshore plays in general, which were more complex, complicated, subsalt, subbasalt, subvolcanics, karsted sediments, and suddenly all the methods for multiple removal, as soon as you went to deep water, decon stopped. All you needed was deep water, and all predictive decon stopped, even if you had a horizontal water bottom, that it was the generator. So suddenly the workhorses of the seismic capability for multiple removal shut down. In addition, the modeling and subtraction methods, and that's very important, the modeling and subtraction, which is an indirect method to try to remove multiples, failed, simply failed. The reason they failed is unless you had exact information of some model type about what generated the multiple, you actually could cause more multiples in the modeling and subtraction than you began with. So that was a, so due to the trend in exploration seismology to more complicated plays, deep water, subsalt, subbasalt, karsted, subvolcanics, where you had complicated boundaries, rapid, vertical, and lateral heterogeneous media, methods that required subsurface information failed. They failed for multiple removal. And the bottom line is they're failing today for migration, yes, which remains dependent on finding a medium model of the subsurface. So this tree represents what MOSRP does for every step in the processing chain. And this annual meeting, as you know, went through every step because this group takes ownership of every step in the processing tree that data goes through. Nothing is not our business because these earlier steps, there's a high bar on the ability to perform those effectively in order to have effective capability delivered from methods further down the tree. So every item on this tree, the green dots represent Green's theorem. The yellow dots represent inverse scattering series. The green dots up on top represent Green's theorem for wave separation methods. This green dot over here is the only green dot that is representing Green's theorem for wave prediction, an ingredient for a high-end form of conventional migration. Every dot on this chart is direct. There is no model matching, there's no searching, there's no seeking. When multiples are removed, free surface or internal, there is no seeking. Okay? There's an algorithm that says you put your data in and you predict the multiple. Okay, so at every step here, these are direct inverse methods, including this green dot. It has different requirements than every other dot on this chart, but they're all direct. There is a role for direct and indirect methods in the real world. Our view is direct inverse methods provide a framework, a clarity, a definitiveness. You actually know that you have a solution. The simple analog is the quadratic equation, x equals minus b plus or minus. You give me a, b, c, you have x. You're not searching for x's. Okay? And so there is confusion today in inversion theory where model matching, indirect methods, are actually considered the only way to do inversion. Our view is if you can describe the physics, in other words, in every real world situation you write some model, some physics to what you assume is the process. The real world is never captured by your physics. There's a piece of it that your physics captures, and there's a piece that's outside your physics, that's beyond your math physics formulation. Our view is, for whatever you can formulate from physical theory, from math physics, you should use direct methods. Indirect methods are there for what's outside your physics. You have no equation. So what else to do other than to seek and search and hope? Yes? So our view is that while you need both direct and indirect methods to be effective in general, that the balance between those two is out of sync. That there is an over-reliance on indirect methods, almost a religious orthodoxy, that model matching is inversion. Nothing could be further from the truth. Okay? And one of the things we'll explain at the end of this meeting is how different they are. Okay, so with those introductory comments, with the exception of this one green dot, which is a contribution and advance to current migration methods that require subsurface information, an advance of significance. With that exception, every other dot on this chart, every other step that the data goes through is not only direct, but does not require subsurface information. I'll repeat that. With the exception of this advance in current migration concepts to what we call Stolt extended Claerbout 3 for heterogeneous media. We'll say some words about that. With the exception of that, everything on this chart is direct, there's no search, and in addition is achievable without subsurface information. Why is that important? Because a minute ago I mentioned that given the trend in exploration seismology, it's increasingly difficult to provide adequate subsurface information. Yes? And one of the reasons that inverse scattering series, internal multiple and free surface multiple has standalone capability today is it does not require subsurface information. Yes? So we need to understand the boundary between what we consider responding to that problem of subsurface information, what has been delivered, and what yet needs to be delivered. Okay? So we're going to point out some highlights. We've just chosen 5 highlights from within the program that you just saw reviewed. We're not going to provide examples or detail. We refer you to the videos that precede this one, which go and describe in great detail what these different highlights are about. So there's work high up in the processing chain. This work is by Jingwu, which takes the need for separating reference wave and deghosting data to onshore, and in particular has made a very significant contribution to that wave separation, allowing an effective separation and removal of ground roll, for example, without damaging reflection data, without needing traction. In other words, a straight-ahead Green's theorem in that context, in that setting, wants displacement and traction. Traction requires derivatives in every direction, lateral and vertical, of displacement, typically not available. So that would be an impediment in practice to being able to remove ground roll without damaging reflection data. What Jingwu has developed is a method that is effective, that can provide that delivery of removal of ground roll and preservation of reflection data without requiring traction. Okay? So that's an extremely important delivery, because if you don't get that step right, everything that depends on it is going to suffer. Okay? Is it glamorous? No. Do people get hired from this group when they work on those kinds of methods? Rarely. Oh, we don't do deghosting here. The issue is, if you have someone who can do this effectively, they can do anything effectively. If they can do that in an innovative, creative resourceful way, they can be assigned to any problem and apply that same set of characteristics to solve. So we take ownership of the whole chain, as I mentioned, and Jingwu has made a major contribution to onshore application. So you might not be interested in your processing in all of these steps that we undertake and how we go about benefiting from that to remove multiples and to image and invert primaries in the way that we pursue those goals. You might have other goals, but if you are interested in removing ground roll for whatever purpose without damaging your reflection data, then I suggest that you take a look at the contribution that Jingwu has provided. Okay. Another important category of activity here is many procedures in those early steps of reference wave and scattered wave or reflection data separation and deghosting assume a horizontal measurement surface. The contribution of Zhenzhang and Yuchang have advanced those wave separation methods based on Green's theorem to allow non-horizontal acquisition. That's particularly important for onshore and ocean bottom. It's of value for towed streamer, but it's often mild, that variation, where if you're onshore and you have wadis and a variable ocean bottom topography, that's assuming it's horizontal, and when it isn't, can have serious negative impact, injurious consequence to all subsequent processing. And Zhenzhang and his colleague Yuchang have shown not only the consequence of ignoring the non-horizontal acquisition, but providing capability that accommodates non-horizontal. And so that's a deliverable that is very important. Again, it's important on its own, and it's increasingly important for all subsequent processing that depend on effective those early steps. Okay, Jingwu in the slide I just raced over, she extended those wave separation methods for non-horizontal acquisition to allow the actual data on your measurement surface to be wave separated, okay, by a combination of Green's theorem and wave equation prediction. So it's a combination of wave separation and wave prediction. And then Yuchang Shen showed numerical examples of that benefit. Another major topic of tremendous significance is the work that's the point man on that work is Yang-Li Zhou. Yang-Li Zhou picked up work that was first discussed with Adriano Ramirez and then made in concrete contributions by Wilbur Herrera, and then for 1D and a single generator to turn the internal multiple attenuator into an eliminator. And last year, Yang-Li Zhou developed a 1D eliminator for all internal multiples from all reflectors. This year, Yang-Li Zhou, together with Chao Ma, developed the first internal multiple elimination method that is direct, of course, and requires no subsurface information. When is that important? If you have a multiple that is interfering with a primary, the currently available methods from all service companies in the world that benefit from what we have delivered in the past will fail. Let me repeat that. If you have a primary that's interfering with an internal multiple, then all of the current methods that the current capability from companies like, for example, Schlumberger, CGG, PGS, that give credit to the services they provide as having derived from what this group has delivered. That delivery will fail. Why? Because that delivery predicts the precise time and approximate amplitude of an internal multiple. And then what is required to remove the multiple is you come in with an indirect method, an adaptive subtraction based on the following concept, that if you have a multiple in your data, and if that multiple is not there because it's been removed, then the process of removal will reduce the energy in the given region that that multiple resides, in some interval of time and in some space of offset. There will be a minimum energy, and that is the current state of internal multiple and free surface multiple application. That is the most effective strategy today for eliminating internal multiples based on methods derived here, but that will fail if you have primary and multiple interfering, because if you have a primary and multiple interfering, you could have destructive interference. And when that multiple is removed, the energy in an interval will increase, not decrease. So it's not the application that people argue about what LP norm should we use for adaptive subtraction. The whole criteria of energy minimization is inappropriate. So that, to respond to that kind of problem, which occurs everywhere in the Middle East, it occurs in the North Sea, occurs offshore Brazil, occurs offshore Australia, and many other onshore applications we've seen in Canada. It's not an anomaly. It's a very frequent occurrence that a primary and internal multiple will be interfering. A target primary and an internal or free surface multiple will be interfering. The strategy that we came up with is you have to have more effective pre-processing. So the work that Jingwu, Yuchang, Zhen we described are all aimed at more effective onshore pre-processing. Get that reference wave separated, get ground rolls separated and removed, so you have reflection data. And then you need an internal multiple eliminator, not something which gets the exact time and approximate amplitude, but the exact time and exact amplitude of that multiple. So you surgically remove it, yes? And you don't damage the target primary. In other words, you reduce the burden on the adaptive step. You build a stronger prediction so that any mischief on the adaptive step will be reduced. And finally, you need a different adaptive criteria, not energy minimization. Locate a property of the internal multiple code itself, some invariance that aligns with its goal, so that when that property is satisfied, and it won't be energy minimization, that the adaptive and the prediction work always in cooperation. Okay? So more effective pre-processing, internal multiple elimination, and an adaptive criteria that derives from and aligns with the method it's meant to serve. So that's our strategy. So this is a landmark contribution of Yang Guizhou and Chao Ma, multi-dimensional internal multiple elimination without subsurface information. Direct, no search, but it needs all those prerequisites to occur. Yes? Okay, so that's bullet 2. Again, all the details and examples and theory behind this are in the previous presentations of this annual meeting. Okay. Jinglu Lin, among the many contributions she's made, is there's often a concentration on what is the dimension of the Earth that you're looking for in some internal multiple algorithm. did you assume the Earth is 1D, 2D, 3D? And less focus is placed on what are the consequences. Well, if you say you have a 2D method, you're assuming a line source. It might be that the Earth in some location is well approximated by 2D, but the lesson that Jinglu Lin has taught us is that it is not a reasonable assumption to assume a line source. That if you're looking for effective internal multiple removal, whether it be free surface or internal, no matter what the dimension of the Earth, you assume that you need a 3D source in that algorithm to have an effective attenuator and then consequently eliminator. Okay, migration methods, traditional conventional migration methods are a good starting point for discussing wave theory migration methods is John Claerbout's 1971 geophysics paper, where he lists 3 imaging principles. In other words, wave theory methods to perform migration have 2 components: some kind of wave theory activity, and then an imaging principle to actually locate structure. There were 3 principles listed there. He made no claim that they were principles that he developed, but they were in the paper and in that paper. So the first is the exploding reflector model, which Dan Lowenthal et al. Developed. It's only for post-stack data. And the 2 imaging principles in John Claerbout's paper, 1971, that relate to pre-stack data. One is we call Claerbout 2, which says take your reflection data back, take the source wave field forward until those 2 are time and space coincident. And when they are time and space coincident, you have located a reflector. That's what Claerbout 2 imaging is by the label we assign to it. Claerbout 3 imaging principle is predict from surface sources and receivers what would a source and receiver experiment produce at depth. After you predict what a source and receiver will predict what would that experiment be at depth, then you ask, make the source and receiver coincident and ask for time 0. And if you ask for time 0, there's no time for that experiment to have any influence from the properties of the Earth that are far from that coincident source receiver, because its time is 0. So you're getting some local indicator, is there structure? Okay, so that's a 0 offset, time equals 0 was the basis of Claerbout 3. Claerbout 2 and Claerbout 3 both evolved. In the early days for at least 10, 15 years, all of Claerbout 2 and 3 were all only viewed in terms of one-way propagation. One way meant that there was a wave that went down and there's a wave that went up. Not necessarily vertically down, but didn't go down and up. A big step occurred in 1983 in Claerbout 2 when Whitmore, McMecken, and others took Claerbout 2 and turned it into allowing waves to no longer be one-way propagating. By saying, instead of saying we're going to take the measured wave back in depth and the source field forward in depth, Whitmore et al. Said, let's take the data back in time and the source field forward in time and look for time-space coincidence. That step led to allowing back in time, allowed for Amical to explore and exploit the overthrust belt. And so that was further extended to allow some geometric optics reflection coefficient by Yu Zhang and Sheng Zhu, Norm Bleistein, some 10 years or so after that, allowing a geometric optics reflection coefficient to be the relationship between this data that went back and the source field that went forward, to assume that at depth there's a geometric optics relationship between them, and hence that RTM, which is the current industry standard, output a geometric optics reflection coefficient. A geometric optics reflection coefficient, first of all, assumes that there is a reflection coefficient. There is only a reflection coefficient for structure in the earth when you have a horizontal or a flat structure. If you have this, there's a reflection coefficient. If you have this, there's a reflection coefficient. If you have this, you don't have a reflection coefficient. If you have a pinch out and you're interested in imaging that point, that very serious and significant point, there is no reflection coefficient. So the whole current top of the line RTM coming from Claerbout 2 doesn't have a structure model that can accommodate curved or diffractive generators of reflection data. Claerbout 3, the predicted source and receiver experiment at depth, at making them coincident and then asking for time equals 0, evolved and was extended by Bob Stolt and colleagues around him in two ways. One that allowed for amplitude information, not just structure, called migration inversion with a dash like NMO stack, and migration followed by inversion. And the second, equally important contribution to that Claerbout 3 that Stolt et al. Contributed was there was an introduction of a point reflectivity model, a point scatter, if you like, which reduces to a plane wave reflection coefficient, not geometric optics, when there is a plane wave structure, and when there is a curved or pinch out, provides a point reflectivity, which allows you to image and invert that reflector where there is no reflection coefficient. So you get an ability to do imaging and inversion with generators of reflection data that current RTM in principle cannot accommodate. Okay, so what has happened in this group? As we said, first of all, those imaging principles, including Stolt's extension to Claerbout 3, occurred at least 15 years ago, maybe 20 years ago. So there's what we have advanced have allowed the benefits that Stolt provided to the extended Claerbout 3 for complex structure, for imaging and inversion, to allow that to occur when you have a two-way wave propagation. That's how we first viewed the contribution that we recently made. So that advance we saw as just initially bringing the benefits of Stolt extended Claerbout 3 to a heterogeneous medium. We were under further examination, in addition to the structural benefits that Stolt extended Claerbout 3 provide for complex structure compared to the current RTM, we discovered that all current migration methods, including RTM, in particular RTM, make high-frequency approximations, and hence do not treat all frequencies with equal effectiveness. That work was shown at this meeting and in a previous meeting by Yang-Li Zhou and Chung Fu, and Chao Ma contributed to that effort, showing that not only are there structural differences in capability, but there is an intrinsic in the imaging condition itself, independent of how you implement RTM or how you extend RTM. The whole concept of Claerbout 2 is high frequency, and hence is not equally effective for low and high frequencies. In That's of interest all by itself. In addition, there is an industry interest in broadband data, where people are paying money to acquire data at lower frequency, and they expect to get benefit from that that acquisition into lower frequency. Well, how do you know whether there's benefit? When you have some kind of prototype image, it looks like some kind of band-limited delta, yes, delta function, and there are these lobes, well known to people in migration. When you add low frequency to the data, just to the data, what you see is that the lobes diminish, and the lobes move in and diminish, hence improve the resolution you would expect. The data that broadband collects sees that difference. We have heard reports from more than a few companies that they're paying money for broadband data. They're seeing the difference in the data. They're not seeing the difference after they migrate. They're not seeing the difference in either resolution, either no difference or small difference. So with that, we thought, well, it must be something that the migration is doing that's not getting the allowing full benefit. It's so knowing that, demonstrating that that current RTM, which is the workhorse and top-of-the-line migration today, considered top-of-the-line migration today, is a high-frequency approximation, makes it understandable that somehow the benefit that you see in the data is not being delivered at the target in the reservoir through migration. The migration method today is not treating all frequencies with equal effectiveness. So there was a study, a comparison of the imaging principle of Kleber 3 and 2, and 2 is behind RTM. You could see that 2 was making high frequency approximations and Stolt extended Kleber 3 was not. That so we saw it in some qualitative sense. The work this year that was presented by Chung Fu and Yang Li Zhou quantified that difference. In other words, by examining the difference in the lobe, these lobes with conventional and then broadband data, it was shown with analytic data and analytic application of RTM and Stolt extended Kleber 3, that for RTM, the lobes reduced by 20%. For Stolt extended Kleber 3, the lobes reduced by 57%. That's significant in terms of resolution, and in addition, those tests made no high-frequency approximation in how the imaging principles were implemented. All current implementations of RTM all make high-frequency approximations. In addition to the principle, the implementation of the take the data back and take the source field forward are making high-frequency approximations. For example, if you're assuming a diving wave like this in RTM, and you're say, oh, well, that's two-way propagation. At every point in that trajectory, if you're assuming the wave went down, 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 up, up, up to the reflector, if at every point you're assuming the wave in this heterogeneous medium is moving in one direction, you've made a high-frequency approximation. That whole model is a high-frequency approximation, in addition to the imaging principle. So we're going to be examining and reporting structural differences for pinch-outs from Kleber 2 and 3, and looking at what actually happens in practice when it's not only the imaging condition, which gives this less than expected benefit from broadband data on resolution and amplitude analysis, like FWI from RTM, but what is the joint collective difference from the implementation methods? So what is new? What's new here is the way we're implementing Stolt Extended Claerbout 3. We're implementing it in a way that does not make high-frequency approximation. And Professor Fang Liu is leading that effort. Okay? So we just went through this. Okay, we gave a review of the inverse scattering depth imaging without a velocity model. In other words, the big step in multiple removal is that the inverse scattering series says you can eliminate free surface multiples. By the way, the Carvalho method for free surface multiple elimination from the inverse scattering series is superior to SRME. Let me repeat that. The Carvalho et al. Free surface elimination method that comes from the inverse scattering series is superior to SRME. SRME, in principle, does not predict the amplitude and phase of the free surface multiple at any offset. It's heavily dependent on adaptive, under perfect conditions, to do the fix. Carvalho's ISS free surface elimination method is, in principle, does not require an adaptive step, for the same reasons that we mentioned earlier. If you have an isolated free surface multiple, then SRME is your toolbox choice. If you have an interfering free surface multiple and target primary, then you want to choose Carvalho ISS free surface elimination, so you reduce or eliminate the need for an injurious adaptive step, which will kill the target primary along with the free surface multiple. Yes. So the inverse scattering series doesn't say that you can eliminate free surface multiples and eliminate internal multiples without subsurface information. It says something much more significant than that. It says you can achieve every processing goal that you can imagine, every processing goal that you can imagine directly in terms of your data, no search, no model matching, without subsurface information. There's an algorithm as direct as the quadratic equation to achieve any goal that you can imagine. Q compensation without Q, nonlinear AVO without overburden information, depth imaging without information, multiple removal. In other words, why did we look into the inverse scattering series to get an internal multiple attenuator? Because we understood, we were the first, Stolt and I, were the first to understand what the potential and promise of the inverse scattering series was. Yes? That it had that message. Locating where that potential is for different tasks is different than knowing it exists. You can prove that there's an uncountable number of irrational numbers, a higher order of infinity of irrational numbers compared to rational. There's no proof, direct proof, that the square root of 2 is irrational. Okay? Very hard to put your finger on it, okay? So that the potential resides, it took 8 years of fundamental and applied work to go from the thought of where the internal multiple attenuator would reside within that. Once we understood the message, locating where that promise and potential is non-trivial. But when you know it's there, it's our job, it's already there. Direct depth imaging without velocity, density, VP, VS is in the inverse scattering series. We're not inventing it, we're locating where that potential is, just as we have with the ISS internal multiple attenuator and now with the eliminator. So there are people who say, yes, we understand the ISS internal multiple attenuator. We understand that. But we also know and understand that you can do ISS, internal multiple elimination, and you definitely can do ISS depth imaging without subsurface information. The truth is, people who say that don't understand any of it. Let me repeat that. People who say that they understand where the ISS, internal multiple attenuator, comes from, but they also understand and are very clear why you can do ISS, internal multiple elimination, without subsurface information, and that you definitely can do ISS depth imaging without information, don't understand any of it. Okay? Because if you understood where the ISS attenuator comes from, you understand what the promise was for the beginning. You understand why we look for it. And if you understand why we look for that, it's exactly the same math physics argument for those other goals and tasks. So either you understand it all, or you understand it not at all. Okay? It's not piecemeal. So for those, why is there confusion? There are a lot of people who confuse model matching with inversion. All of FWI is model matching. Model matching is not evil, it's indirect. Okay? It's indirect. We search, we hope, we got an error surface, we're looking for things to be minimum. You have a direct method, you're not looking, you're not seeking, you're not hoping, you have an algorithm. You put data into an internal multiple attenuator and you predict the internal multiple. There's no searching, there's no iteration, there's no updating. Okay, that's direct. You update the quadratic equation, x is minus b plus or minus. You're not minimizing something. You're not looking for roots. Understood? So that's a very important lesson. Why? Because right now there's a drill success rate in the deep water Gulf of Mexico, frontier drilling, of 1 in 10. It hasn't changed in 30 years. It hasn't changed in 30 years. It's not that multiple removal hasn't changed, it's our imaging concepts haven't changed. The basic thought of needing the velocity to get depth imaging, yes? That was what it was in 1971, and that's what it is today. Okay? The only candidate for making a sea change in capability, analogous to what ISS has brought and is bringing to multiple removal, to bring that to signal, to give you a depth image which is accurate, without needing anything above it, is from the ISS. It has the same exact message and meaning, and we are pursuing it. And we gave a review of that history in an earlier presentation right before this one today, showing the evolution of work with Simon Shaw, Chris Innanen, Zicheng Wang, Jingfang Zhang, and Professor Fang Lu, among others, pioneering ISS direct depth imaging without subsurface information. When that arrives, and we are pursuing that, you're going to have a sea change capability in your drill success rate in the deep water Gulf of Mexico and offshore Angola, okay, and every other place with horrible drill success rates today. It's going to change. My prediction is from 1 in 10 success to 1 in 3. That's what kind of change will occur when that arrives. And when that, if it doesn't occur, it will. If it occurs, it's going to be from this group. And if this group doesn't provide it, no one will. Okay? So that's our significant and serious commitment into the future. The last item here is work with. Well, this is a paper on the direct depth imaging without the first field data, with Fang Lu, Shu Li, co-authored, and with Schlumberger and Statoil, with data that ExxonMobil owned, Kirsten data, showing the promise and potential. The last topic I'm going to mention is inverse scattering parameter estimation. If you're committed to parameter estimation, as AVO and FWI are interested in, and if you're interested in doing Stoltz extended Kleb-Al3 for heterogeneous medium, you're going to need a velocity model. Yes. FWI today is model matching. It's what's the difference between direct and indirect? A direct method, you know that in principle you have a solution. You know if you give the conditions that direct procedure wants, you are guaranteed in principle that you have a solution. So a direct method for elastic changes in Earth properties, for example, including p-wave velocity. There are, from the inverse scattering series, from the pioneering work of Haiyan Zhang, Hong Liang, Xu Li, the main driver was Haiyan Zhang, okay? Identified in the elastic inverse series the direct estimation of changes in VP, Vs, and ρ. There is a term which takes multi-component data and there's a linear estimate in the changes. And another term which is exactly the quadratic estimate that you add to the linear. There's no searching, there's no updating linear. There is a linear, quadratic, cubic, and so on. That's the formula. That's the direct formula for changes in VP, Vs, and ρ. And it requires multi-component data, and there's no model matching, okay? So that is something we're going to pursue because it's going to link, first of all, it's important to pursue it, and there's a paper by Dr. Jinlong Yang and myself, which has been submitted to, who's now at Sinopec, showing a comparison under perfect conditions between what ISS parameter estimation does for a single interface, no full bandwidth, no noise. You can't blame any of the no overburden issues. Just look at what iterative linear, which is a component within model matching, what that does to the direct inverse of the ISS parameter estimation. What's the big, where does inversion, including FWI, get off track? They don't understand that the relationship between changes in properties and changes in a wave field is a geometric series. They think it's a Taylor series. And Taylor series do not have inverses. So they stay at one term, which is linear, and they keep updating linear. If you recognize that the Lippmann-Schwinger equation, the basic equation from scattering theory, tells you that both the forward series and the inverse series are geometric, then you don't have to take linear and update. You have a linear, you have a quadratic, you have a cubic, explicit direct solutions. It is the fact that all mainstream inversion, both within seismic exploration and outside, see the relationship between changes in properties and changes in a wave field as a Taylor series relationship. It is a Taylor series. It's a very special Taylor series called the geometric series. And geometric series have inverses, and Taylor do not. So with that, I will end by thanking you for sitting through this two-day meeting and for giving you some sense of where we have been in this talk, where we have been in seismic exploration, where we are today, and what the a preview of the future. The preview for the future is the following. Bring the capability for imaging primaries that have been delivered to the removal of multiples. When you do that, you're going to have a sea change of effectiveness. Thank you for your encouragement and support.